So the lesson gives us a chance to look at exponential growth, but using the context of a story. And in this case, the story is there's a bird who finds out that when he taps on a red dot on his bird feeder, the seeds come out in a particular pattern. And the students have a chance to discover the pattern on their own by looking at the first couple of times that he taps at the bird feeder. This is Bluebird. Recently, he discovered something interesting about the bird feeder where he eats. The first time he taps at the red dot, a single seed is dispensed. 1. Would you like to add that to your sheet? Okay. The second time, 2 seeds come out. The second time 2 seeds come out, what do you think is going to happen when he taps it a third time? What do you think, Shiloh?
3 seeds are going to come out.
You think 3 seeds? Why?
Because it's a pattern. It's going up by 1.
There's a pattern where it's going up by 1s? Okay. Lauren, Michael, what were you going to say?
I was going to say the same thing as when we a pattern that goes 1.
Okay. Feels like we're starting a pattern. Okay. Do you have a different thought?
Yes.
What?
It smells like thought. I know. I think that it's going to be 4 seeds.
Why?
Because if you could do, so if he taps it, he'll do, it's 2 times 2, which is 4. And so, and there's 2 seeds right there.
Okay. So it's, so that's 2. Did that work from going from 1 to 2 also? Did that pattern you're talking about work from 1 to 2? Okay. Okay, so let's see.
That's right.
4 seeds are dispensed. So go ahead and add that to your sheet. Oh, you already did. Can we predict the next number, right? So when we describe the pattern, when you're describing the pattern, I want you to try to be as specific as you can about what is doubling. I see the word doubling on a lot of people's papers, which is great. What is it that's doubling? What would you say?
I said the number of seeds is doubled.
Doubles, the number of seeds doubles each time. And so when Sims describes it as multiplied by 2, so Louisa said it doubles, Sim says multiplied by 2. Is one right, or
They're the same thing.
they mean the same thing? So we could write either one. The most important thing is we're trying to be specific about what exactly it is that's doubling. So now what I want to do is we've clearly found a pattern, but I want to see if there's another way that we could write the number of seeds and still keep a pattern. So if I ask you, and this is where your whiteboard could come in handy because you might want to just kind of think of some ideas before you write it on your paper. If I ask you to write the number of seeds, the number 2, in exponential form, before you call it out, can everybody think it for a second? What might it look like for the number 2 to be written in exponential form? Can think quietly for just a few seconds. If you want to write something down, you can, but then I'll ask for some ideas. In this lesson, I have a chance to really make that pattern recognition explicit. It's pretty clear to the students that that's a purpose of this lesson, is to identify the pattern. But then we also get to go on to thinking about if we wanted to be able to talk about how you could describe this pattern to others, we get a chance to talk about how to write an algorithm and then also how to abstract that idea into an equation. So there's a lot of very natural connections between the math concepts that we're working on and also computational thinking. Now we're going to get into another computational thinking. So we've done pattern recognition, we've done pattern extension. Now what we're going to look at is something called writing an algorithm. So here's our definition, and you've got this on your sheet too in case you need to relook at it. But an algorithm is a set of specific instructions that solve a problem. That's the definition, right? So it's often written in step form like a recipe for making cookies. So I think a recipe is the easiest way to think of an algorithm because, you know, we do things in a specific order. We solve a problem. I need cookies. Here's how I'm going to do it in this specific order. So how is that going to connect to what we're doing? Well, if you were going to tell somebody how to write the pattern of what's happening to the number of seeds as we double, what would you tell them to do first? And we're going to stick with doing this pattern, the one in the exponential form. What would you tell them to do first? And then what might you tell them to do next? Don't read into the fact that I gave you 3 lines. Okay, I'm not saying that there are 3 steps it needs to be. You can decide how many steps it should be, and if it would be more, that's fine too. Okay, but that's what is called writing an algorithm. So I want to give you and your partner a chance to talk about that. Think about what would the steps be of how you could find the number of seeds each time it doubles. So it's a little different than recognizing than describing the pattern, right?
We thought it just said how to find the number of seeds, so we said find it and then double it and then like, you know.
Find it, double it. I like it.
Find your answer was the last one.
Yeah,
Okay.
find your number, double it, find your answer.
Yeah.
Okay, so we might need to be a little bit more specific, right? Because where do they need to know where to start. So if you look at, I've got this up here so you can see them all together. What would you tell them to start? What number would they start with?
Number of doublings, right?
Okay, and where is that going to show up though?
In the exponent.
In the exponent. So should I write the exponent first? Would
They
that?
should start with the base.
No, the base.
Okay, so maybe we need to
Put
tell
a
them
2 down
as your.
as your base.
Okay, that would work. What's the next step, Laura Michael?
You want to find the doublings, and then the number of doublings will be your exponent.
Right. Find the number of doublings and use that as your exponent.
Is it okay if we switch step 1 and 2? Because we switched step 1 and 2.
What do you all think about that? Can we write our exponent first and then our base?
Well, you don't really write like 3 and then write 2. You write 2, then 3.
We were just saying like look at your number of doublings and then use 2 as your base. Like don't write it yet. Just like
So if we find it, then we use 2 as our base. Do we need a third step? What would the third step be?
find your answer.
Use the number of doublings as an exponent. So what I would say, Luna, is you're not wrong. Could you have been more efficient?
Yeah.
You could have possibly been more efficient, but what you said is still true, right? So another word we use in computational thinking is something called abstraction. And abstraction is really a process. It's a way of doing something. And what it's going to do is it's going to allow us to break down a pattern that we see and work with only the important parts more efficiently. So you're going to try to write an equation that would be the general relationship that would allow us to know the number of seeds and however many doublings we want to do. So I've given you what I want the variables to be. The number of seeds, that's the total number of seeds, will be S. The number of doublings will be N. I want you to try to write that as an equation.
X is the exponent.
Oh, the number
And
of
X-
times that the seeds double. Wait, that's not a
The
reason.
number of seeds.
So if N is the number of doublings, doesn't that mean that N would change? Because if I had 6 doublings, then my N would be 6.
Number of doublings.
If I have 10 doublings, my N would be 10.
Oh, does it need to be a 2 with an N as the exponent?
What do you all think?
Yeah.
Wait, hold on. Number of doublings.
I'm really impressed by the conversations that I heard about creating this. Is this what we all landed on? Yeah, because this is an equation where what we have are variables to represent the 2 things that can change, right? The number of doublings can change, and when it does, it's going to affect the total number of seeds. The 2 doesn't change because what does the 2 represent? It's the base, and it represents the doublings, which is always doubling, so it's always 2. Okay, I love it. So we just talked about this. The doubling shows up in the equation here. The number of seeds shows up as the exponent, and the number of doublings shows up as the exponent, and then the number of seeds shows up as the answer. So I know not everybody got to this, but the next question, the challenge question was, what happens if we change it? Can we take that same idea and use it for something besides doublings? And what's the answer? Can we?
Yes.
Yeah, because if we actually do triplings, we get a pattern where instead of our base being 2, our base becomes 3. And why is it 3?
Because you're tripling.
Because tripling is 3, right? So the equation would be very similar. It's just that we replace the 2 with a 3. What I really liked from this lesson that I actually saw it more while I was teaching it than I did when I was planning it, was when they were getting stuck writing the equation for what would the equation be if you wanted to talk about any number of doublings. Having the algorithm first made it so much easier to write the equation. If they had just been starting from even just the data table straight to the equation, I think it would have been a lot harder. So even for myself, having thought about how I wanted to intentionally put computational thinking into this lesson, I was able to see, I'm going to do that more often. Let's write in words what we're trying to do with the equation first in step-by-step form, then we'll write the equation. It's going to be a lot faster. So I was excited that I'm going to try to use that even more as well.